Welcome viewers to the 12th lecture of the online course non-traditional abrasive machining methods, ultrasonic machining, abrasive jet machining and abrasive water jet machining. So, today we start with we continue with some discussions on numerical problems that might be solved on the basis of material removal rates in abrasive jet machining. Okay. So, let us start right away with one of the problems. On the previous day, we had solved one problem on material removal rate, where d by delta by d term was being experimentally determined. So, this problem deals with you are working in a manufacturing concern which cuts grooves in metallic bodies. Okay. So, there is a metallic body and you are cutting a groove, it is a brittle material. Okay. It is a brittle material. What is stated is that the groove depth d, as shown in the figure, the d is specified as 4 millimeters deep with a tolerance of 0.03 millimeters plus minus. So, it can have a maximum depth of 4.03 or it can have a minimum depth of 3.97. Okay. These are the extreme values of the groove depth, and it is also provided that groove depth and velocity of grooving, they are related as d equal to k by v. V is the velocity as shown in the figure and k is a constant and d is the groove depth. It is being assumed that the groove width, which is perpendicular to the plane of the paper, that is not affected, neither does it affect this particular relationship. So, and also we are not really concerned about any change that might take place in the groove width due to change in velocity. It is simply being assumed as constant. At present, you are employing a grooving velocity of v equal to 10 meters per minute. So, that means I am grooving now with a velocity of 10 meters per minute and I am obtaining an exact depth of groove equal to 4.02 millimeters. So, it is acceptable because it is lying within the range 3.97 to 4.03. However, due to running of another machine nearby, a vibration is introduced into the table as shown with displacement. Just a moment, this expression of displacement has not come in. Okay. Okay. We can consider it this way, that it has this particular vibration has an amplitude of 0.03 millimeters and with an angular velocity of 50 pi radians per second. Okay, 50 pi radians per second. So, if you still go on cutting the grooves, will they be accepted? So, what do we have here? The amplitude is given to be 30 microns and the angular velocity is 50 pi radians per second. Okay. So, in that case, if there is a vibration introduced, will the cuts be acceptable? Will the grooves still be acceptable? Now, what is going to happen here is this, that if you now look at this particular piece of paper. So, if there is, this is the say top surface of the metal piece, and I am having a grooving velocity of this type. But if there is a vibration set in on the table while the grooving element, the nozzle, that is still at the constant velocity, therefore, this velocity will have a reciprocating velocity impressed upon it. So, it will be v plus minus v 1 coming from the vibration. So, if it is of considerable amount, we will find that velocity will be varying, and due to this changing velocity, as groove depth is equal to k by v, as this is now changing, we will thus have a change in groove depth. Groove depth will be like this. So, we need to find out what is the maximum and minimum groove depth. This is the minimum and this is the maximum, whether they are within limits. So, as easy as that. So, let us have a look at the answer. So, what we know is, let us find out the value of k. If depth of groove is equal to k divided by the velocity, we can say that depth of groove 4.02 millimeter, 4.02 millimeters divided by 1000 to make it meters is equal to 60 into k by 10. Why this 60? This must be 10 meters per minute. If 10 meters per minute is the velocity, 10 by 60 is the meters per second, and therefore, k comes out to be 4.02. This 0 and this 10 cancels out. So, 6000 at the denominator. K is equal to 4.02 by 6000 equal to 0.0067. Okay, that is understood. K has been found out. So, now we try to find out the highest and the lowest velocities. Highest and the lowest velocities will be equal to velocity of grooving, which is still 10 meters per minute, and also the vibrational velocity which is introduced, and it will first be the maximum and minimum values are once it is subtracted and another time it is added. They will define the minimum and the maximum velocities. So, that velocity of grooving is 10 by 60 meters per second plus minus a omega. If the viewers kindly recall, a omega gives us in simple harmonic motion the velocity, the maximum velocity at the mean position, where a is the amplitude and omega is the angular velocity. And therefore, once we put in the values of omega and a which are given in the problem, we will obtain that the maximum and the minimum velocities will be coming out as 0.1713, 0.1713 meters per second and 0.1619 meters per second. And the corresponding depths can be found out by putting their values in the d is equal to k by v. Sorry, d is equal to k by v. So, d 1 comes out to be 3.91 and d 2 comes out to be, the two extreme values, they come out to be 4.13 millimeters. Therefore, obviously, it is not within the range 3.97 to 4.03 and is not acceptable. Okay. So, it is not acceptable. Next, now we take up a problem on performance index estimation, machine performance index. In a company carrying out EGM of brittle materials, one machine is working slower than predicted I should say apparently working slower than predicted, and its performance needs to be checked. So, what is the problem? Somebody has become doubtful about the performance of a particular AGM machine, and in the competitive market, if you are lagging behind, then you might be eliminated, hunt or be hunted, a rat race. So, the company needs to check the performance of the machine. The company defines an index of performance. Okay. So, they define, okay, I will check this particular index and I will decide accordingly whether the machine is working all right or not. The company defines a performance, an index of performance equal to volume of work material removed per kg of abrasive, volume in cubic meters of work material removed per kg of abrasive. So, it is quite easy to understand. I am removing this much amount of material, but I am having to spend this much amount of abrasive for that, and this I am defining as my performance index. I will check that. If it is going down, it is bad. If it is going up, it is good, and starts monitoring it over time for that AGM machine. Utilizing this index, find from the table below whether the performance of the machine is improving or deteriorating with time. So, what does that mean? That the machine must have been checked over time for a number of occasions, and this index must have been found out, and from that, or rather you have to find out this index and decide whether the machine is working, whether it is working slower than predicted or not, etc. So, let us see this, what is provided, that is quite interesting. So, first of all, date of experiment. Date of experiment says that in 2009 there was one experiment. Exactly 1 hour, 1 year after that, let us not go into the possibilities of leap years occurring, okay, just 1 year. So, date of experiment 2609, date of experiment 2610, that means 2010, and date of experiment 26/2011. So, time wise there is absolutely no problem. We are measuring the performance after 1 year, and we have taken 3 measurements. Okay. So, that is easy to understand. Abrasive grades, they are spent, the abrasive grids have been used up at the rate 2 grams per minute in the first case, 2.5 grams per minute, and 1.9 grams per minute. You might say, why is there this discrepancy? Why don't we have 2 grams per minute flat? That is because for different types of operations that might have been required, the machine had to use up abrasives at different rates. So, you cannot really help that. Okay? Just we have to accept, okay, different rates of expenditure of abrasives had to be there in order to meet with different requirements. Jet velocity was also different, 200, 175 and 160, as we discussed, for different requirements that might have been there. Density of abrasives also was different, 3000, 3500. Okay. So, these things were different for the different years, and workpiece density has been given to be 3000, and hardness to be given has been given as 4 GPa, and material removal rates are 7 into 10 to the power minus 10 meter cube per second, 7 into 10 to the power minus 10 once again, and 5 into hopefully 10 to the power minus 10. Okay. So, apparently offhand a person examining this table might come to the conclusion that material removal rate is coming down. But here we should remember one thing, that the main thing we should notice one thing which is of primary importance, that is the input conditions are not the same. We cannot compare these mere values. Okay. Just like that, flat comparison is not possible because the inputs are not the same. Okay. So, best is to check up what is the predicted MRR in all these cases separately and compare it with the experimentally obtained values in the last column. So, let me make it clear, all the abrasive grit details, they are input conditions, workpiece details input conditions, while MRR at the last column is experimentally obtained. Let me just emphasize on this. These are experimentally obtained values and these are all input conditions. So, best thing would be from the input conditions find out the predicted output and compare it with these experimentally obtained values. That is it. That will be the best check instead of flat comparison between these values. That would be wrong in fact. Let us have a look how this is done. We know that MRR of a brittle material is proportional to, or rather we can also say it is equal to 1.04 into m dot A. M dot A means the abrasive mass flow rate multiplied by velocity of the gas jet to the power 3/2 divided by density of the abrasives to the power 1/4 and hardness of the workpiece to the power 3/4. Now, if this is the MRR, the performance index would be divide the MRR by the mass flow rate of abrasives. So, simply mass flow rate of abrasive will vanish and it will be V to the power 3/2 divided by rho g to the power 1/4 into h to the power 3/4. And therefore, we have put in the values. Let us see, the first theoretically predicted value of the performance index is how much is that? 200 to the power 200 is the gas jet velocity to the power 1.5 divided by rho g 3000, okay, density of the abrasive grits 3000 to the power 0.25 multiplied by hardness of the workpiece, okay, 4 GPa. So, that converted to pascals multiplied by to the power 0.75 and all sorts of number crunching gives us 2.4 into 10 to the power minus 5 meter cube per kg. Okay, that is understood. 2.4 into 10 to the power minus 5 meter cube per kg of abrasive. Now, let us see the experimentally obtained value. What is the experimentally obtained value? The actual experimentally obtained MRR divided by the consumption of abrasives. So, that value was 7 into 10 to the power minus 10 divided by 2 into divided by the consumption of abrasives. Let us quickly have a look by going back. Consumption of abrasives. Consumption of abrasive was 2 grams per minute. So, this has to be converted to 2 divided by 1000 into 60 for per second and 1000 for changing grams to kgs. So, all this multiplication leads to 2.1 into 10 to the power minus 5 meter cubes per kg. So, fraction of performance, which means that the index which has been found out theoretically is higher than the index which has been found out experimentally. I mean the experimental performance is not as good as the theoretical one, that means the predicted one, and therefore, it is working at 0.875 fraction of its predicted capacity. 0.875, let us remember this particular fraction. Now, let us take the second case. Second case, we have to carefully see whether we have introduced or incorporated the changes which have occurred due to different input conditions. So, let us remember we are taking velocity to be 175, density of the abrasive to be 3500, and workpiece hardness remains the same. Okay, let's have a quick look. Right, the velocity has been taken to be 175. The abrasive grits are, consumption is at 2.5. Is that important? No, that's not important, but the density of the abrasives is 3500. This is important, and 2.5 will be occurring when we find out the experimentally obtained value. It should be 7 into 10 to the power minus 10 divided by 2.5 by 1000 by 60. Okay, let's have a look now. Yeah, so the green one is the second case. So in the second case, velocity is coming correctly 175, 3500, 4 GPa, and all this number crunching gives us finally the value 1.89 into 10 to the power minus 5. Okay, so this is the theoretically predicted value of the performance index. When we find out the performance index as per the experimentally obtained values, 7 into 10 to the power minus 10, okay, and 2.5 as we have rechecked from the table, this divided by this gives us 1.68 into 10 to the power minus 5. So here you can observe that compared to the previous value, the experimentally obtained value is still less. Okay, it's still less, but if we take the fraction of performance, it is higher than the previous value. So surprisingly, the machine appears to have improved in its performance in the second year. The machine appears to have improved in its performance in the second year as per the value of the performance index defined. Okay. What about the third year? That I have left for you to find out. I did find it out, and it appeared that it went down again. Okay, it went down again. So now that the idea is clear to you, I am sure that you can work it out yourselves and come to a solution and a decision that yes, whether the machine is performing all right or not. Okay. So I hope that this is clear and you did understand and enjoy the problem. So let's move on to the next one. Okay, this is interesting, but unfortunately it's not coming fully on the screen. What do I do in order to get it? Okay, let me see. I can read it out in case you have a problem. Just one moment. Yeah. Your neighboring country, okay, your neighboring country has purchased an anti-aircraft gun with a muzzle output velocity of 560 meters per second. Okay, I will write it down here when we come back to this one. 560 meters per second is the muzzle velocity. So let's draw a gun. Okay, this is your gun. It looks more like a telescope, but please be a little imaginative and bear with me, my drawing, and understand and imagine that this is a gun rather than a telescope. The science has both applications, destruction as well as research. So this is a gun and out comes the bullet. Okay. So I think the bullet has been defined as round, okay, perfect bullet, I mean perfect shape, comes out this way, and at this point it has 560 meters per second, quite a reasonably high velocity, and the projectiles are of spherical size and made of solid iron with a density of 7.6 grams per cc. Are they made of solid iron in reality? Perhaps not. They must be full of explosives and they burst. Anyway, for our problem, they are made of solid iron with a density of 7.6 grams per cc. Your army helicopters are being targeted. and the Defense Department asks you to determine the flying height at which the indentation damage depth delta can be a maximum of 5% of the projectile diameter. Oh my God, what a complex situation. The helicopter body is covered with TiB2 plates of hardness 3500 kgf per millimeter square, and here you can apply the theory of damage caused by abrasives as in AJM. Oh, now it is understood. Herein lies the link to our problems here. So, first of all, let us draw a picture here, what is being what is being suggested. So, first of all, I make an assumption that in order to get the rise to the maximum height, you have put the gun this way. Okay. So, this is the gun, this is coming out 560 meters per second, and this goes up, and this is your army helicopter. So, the army helicopter, it is being assumed that yes, in the worst case is that the army helicopter is going to be hit, and if it gets hit, there will be a damage, and this damage can be the tolerable damage is 5% of the projectile diameter. Okay, that is understood. So, if that damage is 5% of the projectile diameter, what should be this height which will restrict this damage to that particular value? This is the problem. What is this height at which we will fly very safely, feeling very safe at least, even though you get the jolt of the projectile hitting you, you will be sure that whatever you do, you are not more than 5%. That is what. Let us have a look at the calculations. First, apply the theory of kinetic energy of spherical iron projectiles equal to plastic energy, strain energy of the helicopter body armor. Remember, the helicopter is covered by TiB2 plates which have some 3200 kgf per millimeter square or something like that. So, we will come back to those values later on, but first of all, let us see what has been tried out here. First of all, half mv square. How is this half mv square? This is half. Now, where is that? Yes, this is half, this is density, this is volume 4 by 3 pi r cube, okay, multiplied by the velocity square. So, this is the energy carried by the iron what do you call it, spherical iron object, missile or bullet at the point of hitting, the point at which point in time when it hits, it is having this particular kinetic energy, and this is equal to half into projected area of plus indentation multiplied by the hardness of the damaged armor plate multiplied by the indentation depth. Okay. So, this is the full expression, and after that I think we have introduced some simplifications like d square. We already know d square is equal to 4 into d into delta. This we have done so many times. Okay. So, this we are quite conversant with, we have no issues with this, but now we are introducing the condition which has been provided, that is delta can be replaced as 0.05 of the diameter of the spherical iron projectile. That is good. So, d by 20 is equal to delta. The moment to do that, how many deltas do we have? We have two deltas here, delta square. So, we have delta replaced by d here, and also a 400 coming from the two 20s at the denominator. So, that is it. We have quite a reasonably simple expression. So, what do? We have d cube occurring here and a d cube occurring here. That is good. So, we become free of the d's in the world, and therefore, after that lots of cancellations will definitely occur, and let us see what are the things which are surviving. Velocity is surviving and the strength of the material, that means hardness, is surviving. That is good. So, from here velocity square comes out to be 6h by 400 into rho. Now, what is this rho? This rho must be the density of the iron, okay? And therefore, after putting in all these values, velocity comes out to be 262.8 meters per second. Now, find out the height at which the projectile with starting vertical speed of 560 meters per second will reduce to 262.8 meters per second. In my calculations, it came out to be 12.29 kilometers. This is quite, I think, quite common for aeroplanes, but whether for helicopters this is common or not, I don't know. But for the sake of mathematical calculations, it's no problem. First of all, how do we get this particular height from this calculation? That's quite simple. What you can do is you can simply apply one of those equations. Remember, v is equal to u plus ft, s is equal to ut plus half gt square, and v square is equal to u square plus twice fs. Okay. One of these will definitely give you. Start with this velocity. The velocity is gradually eaten up by acceleration due to gravity towards the other direction, I mean towards the center of the earth, and therefore you will ultimately get this particular velocity solved. I mean, rather, this velocity is provided so that you will be solving for the height, which is coming out to 12.29. I am sure you can do these yourselves. So, we come to the end of the 12th lecture, and in the 13th lecture we will take up other aspects of abrasive jet machining. Thank you.